What is energy? By definition, energy is the ability to perform work. There are two different types of energy: energy that's stored and energy that's in motion. As for energy that's stored, it's known as, excellent, potential energy. More specifically, in this case over here, gravitational potential energy. Well, what about energy that's in motion? That's known as kinetic energy. And if you could see it, it's known as mechanical energy. There is another type of kinetic energy, but we'll cover this in a future episode. So if energy is the ability to perform work, then what exactly is work? Well, work is the transfer of energy from one form to another. There is this very famous formula, and it's known as the work-energy theorem, which states that work can cause a change in kinetic energy, and if you want to have a change in kinetic energy, you must perform work to do that. As for this triangle up here, it is delta, which means change in. So in other words, to determine the amount of work used to speed up or slow down an object, you need to find out its final kinetic energy and subtract it from its initial kinetic energy. Both work and energy are measured in a unit called joules, named in honor of James Prescott Joule, a scientist who worked in the study of energy, more specifically thermal energy, about 200 years after Sir Isaac Newton. What I'm trying to point out is that Isaac Newton, he had no idea about this notion of energy. He had his own version of it, which he called momentum, which is the quantity of objects that are in motion, and it's a vector quantity. All right, but more on that next year. As for now, let's focus on mechanical energy. So what exactly is mechanical work? Well, it's a work accomplished in moving an object by an applied force, and it goes in the same direction that you applied the force at. Often this is described by a force distance graph. So if I apply a light force and I push an object, it should produce a graph that looks like this. And the further I push it, the greater the size or the area of the rectangle. In fact, by definition, work is the area underneath a force distance graph. So if I apply a greater force, you'll notice that the area that's drawn here is much larger. You'll notice that the shape looks like that of a rectangle. In that case, why not just find out the surface area of a rectangle? Base times height. And that's where the formula comes from. Work is equal to the force applied times the distance that it travels. Of course, this formula only works if the force applied is constant. It has to be a fixed value. If this all happens to increase and decrease, then you have this wobbly surface area that you have to calculate afterwards, and that's not fun at all. We'll save that for a future episode. All right. So in all of your homework tonight, it's always a constant force that's applied. And once again, in honor of James Prescott Joule, work is measured in joules. Joules is not a fundamental unit. It's a derived unit by a Newton multiplied by a meter. And a Newton is not a fundamental unit either. If you recall, a Newton is equal to a kilogram times a meter per second squared. So 1 joule is equal to a kilogram times a meter per second squared times another meter, or you could just do meter squared over second squared. These are the fun and exciting fundamental units, and this is the derived unit. So both newtons and joules are derived units. How about when work is not accomplished? Well, if I try pushing against this wall as hard as I can and the wall doesn't move, even though I'm applying a force, as it's not traveling a distance, no work is done. Or what if I'm carrying a really heavy backpack and I'm carrying it in a straight line at a constant rate in the same direction? Well, in that case too, I'm not performing any work. For if my feet were replaced with roller wheels, then you'll notice that it's just the inertia of me that will cause me to move forwards. All right. So if no distance is traveled, you haven't done any work. And if inertia is just carrying you through, then there's no external force being applied. Now the effort in accelerating me, yes, that is when I'm doing work. But if I'm just cruising along, allowing inertia to carry me forwards, then no, work is not accomplished. Let's try a mathematical problem. How much work is needed to pull a heavy box with a force of 8 newtons forwards for a distance of 25 centimeters? While working it out, I hope you recall that we need to solve everything with this in our minds. Distance is measured in meters, mass measured in kilograms, and if there's any time involved, measured in seconds. So let's go and convert that through. 8 newtons times 0.25 meters gives you 2 joules. What exactly is a joule of work? Well, I'll show you that afterwards. Why am I picking my nose? I hate freaking picking my nose. I'm not re-recording. I'm just gonna... When solving this problem, make sure that you have this in the back of your mind. MKS. For distances measured in meters, mass measured in kilograms, and time measured in seconds. So go ahead and work this out. What answer do you get? Excellent. I hope you got 2 joules. All right. And here's all the work used to prove it. Okay. Start with your givens. Show me your formula. Sub everything in, making sure that your distances are measured in meters. And your final unit will be in joules. Well, work can only be accomplished if you're able to move the object. So if I'm dragging it at a diagonal, then unfortunately I'm not able to lift it. Only the horizontal component helps me in accomplishing work. So in this example over here, we have to figure out the horizontal component of the force that enables us to perform work and multiply that by the distance that it travels. You'll see in the setup over here, it does form a right angle triangle, and this red vector is beside theta. So another way of representing this formula here is that work is equal to the force applied times distance times the cosine of theta. So if you work out this problem over here, where I'm pulling at an angle, I'm actually performing less work. Now, work is a scalar quantity, all right? You can't be performing 2 joules of work to the east and then 6 joules of work towards the west, all right? After all, you're going to have this weird net value, which can net to a value of 0, even though you're burning calories. So work is not a vector quantity. Instead, it is a scalar quantity, where if you are doing work, positive work, then the value is positive. Oh man, why is my nose frickin'... Now work is a scalar quantity, meaning that there's no direction. After all, if I walk 1 meter towards you, and then I walk 1 meter back, it's not like I am burning calories this way, and I'm getting slimmer and slimmer and slimmer going this way. That's impossible. All right. But we do have notation. Work is a scalar quantity. I can't be doing 2 joules towards the camera and then 2 joules away from the camera and somehow net to 0 joules of calories being burnt. That doesn't make any sense. That means that if I keep on going backwards, I'll start to get chunkier and chunkier. All right. However, there is such thing as positive and negative work. And by definition, positive work is when you apply a force and it moves in the same direction that you apply it at. On the other hand, if I'm too weak to hold on to this water bottle and it starts coming downwards, I'm still pushing upwards, but the direction is in the opposite direction. So now I am performing negative work. So positive work, negative work, negative work, positive work. All right, let's do this one. Calculate the total work to push a heavy box 8 newtons forwards for 25 centimeters. Unfortunately, you have a frictional force acting on you as well, which then negates the work that you're doing. So let's calculate out the total work. We know that the total work is the force applied, or the work applied, plus the work due to friction. And if you think about it, friction always applies a force in the opposite direction. So friction will always apply negative work. Not that you need to put a minus sign here right now, but you'll see that it will work out to a minus sign. All right, so you're applying a positive force of 8 newtons forwards, and it's traveling 0.25 meters forwards. However, the force of friction is in the opposite direction, also traveling the same distance. So before, when you were performing 2 joules of work, now with friction involved, you're performing less work. So what exactly happened to that 0.5 joules? Well, it's attributed towards converting that energy into something useless, usually that of heat, and that's the consequence of friction. There's also another way of solving the same exact problem without injecting a minus sign in here. And it has to do with using that formula. Work is equal to force times distance times cosine of theta. And if you see friction, friction is always in the opposite direction. It's exactly 180 degrees opposite of the direction that you're traveling. So you could actually do it that way. Okay, you could actually multiply by 2 newtons times the cosine of 180 degrees, because cosine of 180 always equals minus 1 each and every single time. Isn't math neat? All right, so let's go and calculate out gravitational potential energy. What is a numerical value? We'll start off by the definition of work, force applied times distance, and the force that is being applied in lifting something up is equal to mass times gravity. So we have a formula of work is equal to mg delta d, but since this is lifting it up vertically, why not just call it height instead? And that's why the formula looks like this in your textbook. Work is equal to mg times delta h. And once I've lifted up to this height, it now has stored energy in the form of gravitational potential energy. All right, so EP is the amount of gravitational potential energy an object has once you've lifted it up a particular height. So how much work does it take to lift this water bottle up by from here to right where your top of your wrist is? That's about 20 centimeters. Go ahead and calculate it out. Okay, don't forget, mass needs to be measured in, excellent, in kilograms. All right, so EP is equal to mg delta H, or 0.5 kilograms times 9.81 newtons per kilogram times a height of 0.2 meters. And once you calculate it through, you'll get an answer of 1 joule. I really wanted you to experience what 1 joule is, because I know these are just numbers at the end of the day, but I want you to feel it. So go ahead, take one of these environmentally unfriendly bottles, lift it up from here all the way up to here, and now that's 1 joule of work. 2 joules of work, 3 joules of work, 4 joules of work. You'll notice that this value in joules, it's a very small measurement. It isn't much effort at all, at least from our frame of reference, because with an ant, this is impossibly a lot of work to do. All right, but for us, this is near nothing. And that's why there are different scales of measuring energy. All right, in general, we measure it in joules, but there's also a smaller measurement called electron volts, and we'll cover that in a future episode. And in our next unit, when we talk about electricity, if you ever looked at hydro bills, they measured in very large quantities, known as kilowatt hours. So kilowatt hour is a lot of energy, all right? Specifically 3.6 million joules, and we'll prove it towards the end of this unit. All right. Another interesting thing is that joules, there's another counterpart to it called calories, which is nutritional energy, all right, where it takes 4,000 of lifting this up to burn 1 measly calorie. Hope you've noticed that before if you've ever been on a treadmill, right? You turn it on, you enter in your mass, and you walk away, and about a minute later you're wondering, well, how many calories did I burn? And you go, what? 0? And that's the case. It takes a lot of effort just to burn 1 calorie, all right? So calorie is a larger measurement of joules. Okay, so mechanical kinetic energy, how do we derive out that formula? We start off foundationally with this formula here. Work is equal to force times distance. We also know that according to Newton's second law, force is also equal to mass times acceleration. So we get this formula here. And this formula is 100% correct, but it's only useful in one case. If you notice and can observe the rate of acceleration and can measure the distance that it travels during its acceleration, then this formula is useful. But often with regards to kinetic energy, our eyes are closed, and by the time we open it, then we see the object in motion. So this formula becomes useless. All right, so how do we figure out what kinetic energy an object has if we open our eyes and we already see it already in motion? Well, for one thing, we have seen A beside delta D before, and we can get rid of that. Think about what formula had it beside each other. Yeah, this one right over here. So how about we just take this formula here and isolate for A delta D. Now remember, we're already watching the object as it's in motion. So obviously at the beginning it had to start off from rest. So that starts off at 0. So A delta D is equal to your current speed squared divided by 2. Now we can sub this into up here, and that's how we create our kinetic energy formula. Ek is equal to 1/2 mv squared. How we go through an example? Okay, we'll work it through together. Remember, mass needs to be measured in kilograms and speed needs to be measured in meters per second, all right, in order to get to this answer here. Yeah, let's work through this. So Ek is equal to 1/2 of 0.1 kilogram times 0.5 meters per second squared. Don't forget to square this. All right. So 0.5 times 0.5 gives you 0.25 divided by 2 gives you 0.125 times 0.1 will give you 0.0125 joules of energy. Excellent. All right. How about this problem now? How much work is done by accelerating an object that's already in motion from 4 meters per second to 8 meters per second? How about I give you a moment to work that out? Did you get an answer? I hope you didn't. That's not the correct answer. Instead, the correct answer, well, we'll work it out together. No pun intended. You got to keep in mind that the object's already in motion. All right? You can't just simply subtract these two. And the reason why you can't subtract the two is that if you look at this formula over here, energy and speed are not proportionate. In other words, if you double the speed, you don't double the kinetic energy. You double times double, or you quadruple it, all right, as it's squared. So that's why you can't just blatantly subtract 8 from 4 and expect it to work out. Instead, you need to find out how much energy you have at 4 meters per second and find out how much energy you have at 8 meters per second, and you're looking for the differences in them because that's the work that's done in speeding it up from 4 meters per second to 8 meters per second. All right, so work is equal to the change in kinetic energy, which is equal to 1/2 mvf squared minus 1/2 mvi squared. And you can sub everything in. Now, optionally, if you wanted to, I'll just write this on the side, you could technically factor out your m. That's fine, all right? And then you can do vf squared minus vi squared, and that will work out perfectly to your correct answer. But please don't do this. 1/2 mvf minus vi squared. This will never work out. Even mathematically, it won't work out. Remember, vf minus vi squared, if you expand it out, it'll be this. If you remember FOIL, you're going to get vf squared minus 2 vi vf plus vi squared, and this does not look like that. All right, that's the very reason why you can't do that. Mathematically, it doesn't work out, and due to the nature of the relationship between speed and energy, it's not linear. You can't just blatantly subtract them. Okay, you got to sit down and put in the work. Pun intended. Another way of seeing it is taking a look at energy and speed as a graph. All right, you'll notice that it does create this quadratic correlation. And what you're effectively doing is that you're looking at the differences between EI and EF. And that's the work that you're doing. So that's why you got to calculate out what your EI is and what your EF is and subtract the two. Here's one that involves some mathematical rearranging. How about I give you a moment? Okay. Hope you've worked it out to the same exact answer of 40 meters per second. If not, come follow along with me. First off, mass needs to be in. Excellent. Kilograms. All right. And you probably want to convert the 0.2 kilojoules into joules because it'll make more mental sense. Next, we're going to take the formula 1/2 mv squared is equal to Ek and isolate for V. Okay, so first thing we're going to do is we're going to multiply both sides by 2. So we get 2Ek is equal to mv squared. To get rid of the m, we divide both sides by m. Now we have v squared is equal to 2Ek over m. And we need to square root both sides to get rid of the squared. So v is equal to the root of 2Ek over m. Sub in the values for Ek and m. As you can see here, I've gone through it as an animation. and then you'll get your answer. Awesome like possum? Great. Catch you in the next episode.